This is the first video on a new chapter which will be on thermodynamics. So in this video we will discuss temperature. And before even talking about temperature, I should discuss the difference between temperature and heat. In everyday language, heat and temperature are often referring to the same thing, but in physics there is a difference. And in the meaning of heat and temperature are not the same. We will use heat to refer to an energy transfer caused by temperature differences. So to describe a state, we will use the temperature of the state, and to describe exchange of energy, we will use heat. But how do we determine the temperature? For example, in your everyday life, if you touch something and it feels hot, we conclude that it has a higher temperature. And if you touch something that feels cold, then you conclude that it has a lower temperature. But our senses can be wrong sometimes. For example, if you have a piece of wood and a piece of metal, if you take the piece of metal in your left hand and the piece of wood in the right hand, your senses will tell you that the wood feels hot, and the metal, on the other hand, feels chilly. Right? The same thing if you sit on a bench that is a metal bench or a wood bench, even if they have the same temperature, really, you would feel them, the metal bench would feel colder. And if they are in the same room or in the same atmosphere for a long time, you know that they must have the same temperature, right? So your senses can give you the wrong information when you want to use them to measure the temperature. And so that's why we invented thermometers, right? So how do we make a reliable thermometer? First, what do you need for a thermometer? You need a measurable property that will vary with the hotness and coldness of the system. And for example, the ethanol thermometer uses the fact that the volume of a liquid expands with temperature. Another kind of thermometer is called the constant volume gas thermometer, uses the fact that the pressure increases with temperature. Some thermometers also use the fact that the electrical resistance of a wire varies with temperature. And there are also that the radiation of surfaces varies with temperature. And in all of those examples, you have a measurable property that varies with temperature. Now, the second thing that you need for a thermometer is that you need the thermometer to be in thermal equilibrium with the system that you are trying to measure. So keep in mind that the thermometer measures its own temperature. And so if you want the thermometer to give you the temperature of an object, you need to make sure that the thermometer and the object are in thermal equilibrium with each other. So this leads me to mention something that is sometimes it is called the Zeroth law of thermodynamics. If you have three bodies, system A, system B, and system C, and if system A and B are not in direct contact, not in direct thermal contact with each other, but both are in thermal contact with the same system C, then the Zeroth law of thermodynamics says that if C is in thermal equilibrium with both A and B, then A and B are in thermal equilibrium with each other. And A and B in thermal equilibrium is the same as saying that their temperature is the same. Right? TA is equal to TB. Now, finally, the last thing that we need for a thermometer is a temperature scale. So, for example, the Celsius scale that uses two reference points. The 0 in the Celsius scale was taken as the freezing point of pure water, and 100 degrees Celsius was taken as the boiling point of pure water. Now, another temperature scale is the Fahrenheit. Right? Most of the world actually uses Celsius because Celsius is part of the metric system, and most of the world uses the metric system. In fact, only 3 small countries do not utilize the metric system: Burma, Liberia, and the United States of America. But in fact, Burma and Liberia, they use the Celsius scale. There are, in fact, only 5 small countries that still utilize the Fahrenheit: Bahamas, Belize, Cayman Islands, Palau, and the US. So since we live in the US and we use the Fahrenheit scale, let's see how it was defined. There are several stories, in fact, on how Fahrenheit created the scale. So first, let's start with the zero of the Fahrenheit scale. One day during the winter of 1709, in his hometown of Danzig, Fahrenheit said, "Oh, it's really cold today. Let's call this the 0 Fahrenheit." Okay, so that's pretty much how we get the 0 Fahrenheit, the reference point for the 0 of the Fahrenheit scale. Now, then we need a second reference, and there are several stories for that. One is that he used his body temperature and or the one of his wife. But that means that they will have to be sick because that's a little hot. So another story is that he used the blood temperature of a horse. And because he wanted a scale that can be easily divided, he chose 96 instead of choosing 100. And so in this scale, pure water freezes at 32 Fahrenheit and boils at 212 Fahrenheit. And so we use this to define the Fahrenheit scale nowadays. Now, we make fun of the Fahrenheit scale, but it's very advantageous for us because the two references are experienced by the human body, right? It's very convenient to have a fine scale in the temperature range that we experience in our everyday lives. Right? In the Celsius scale, we only have 40 degrees to describe all the temperatures, the kinds of temperatures that we can feel, but we have 3 times more in the Fahrenheit scale. So that's one advantage. So we see that between the freezing and the boiling point of water, there are 180 degrees in the Fahrenheit scale. And so to convert from Celsius to Fahrenheit, we will use the temperature in Celsius multiplied by 100 divided by, multiplied by 180 divided by 100 and add 32 to get the temperature in Fahrenheit. And to get the temperature in Celsius, you take the temperature in Fahrenheit, remove 32, and then multiply by 100, divide by 180. Now, all these different thermometers, they will agree at 0 degrees Celsius and at 100 degrees Celsius, but they don't necessarily agree at intermediate temperatures, right? To make sure that they agree, we need to have a property that varies linearly with the temperature between that range. And that is what led to the Kelvin scale. One thermometer that in fact has a linear dependence on temperature is the constant volume gas thermometer. So in this picture, you see such a thermometer, and I also have one for the demo in class. You have a solid sphere that contains a gas, and there is a manometer to record the pressure of the gas. And when I put the sphere of gas into liquid nitrogen, the pressure decreases. Let's see. Can you move, please? Thanks. When I recorded this, I set the camera a little too far, so we can't really see the needle on the manometer, but it gives you the pressure. And here I'll show you, if you record the pressure of the gas as a function of temperature, for example, with the Celsius scale, you see that it is perfectly linear. And so on this plot, the 3 different lines are recorded for the different amount of gas in the thermometer, and 3 of them are perfectly linear. No matter how much gas there is, the temperature dependence of the pressure is linear. And if you extrapolate to 0 pressure, you see that it would happen at minus 273.15 degrees Celsius. And so the 0 of the Kelvin scale is taken at this temperature, where the pressure would be 0. So minus 273.15 degrees Celsius corresponds to 0 Kelvin. And we can convert between the 2 scales by taking the temperature in Celsius and adding 273.15 to get the temperature in Kelvin. Note that this relation means that the Celsius and the Kelvin scales, they have the same size degrees. Because the pressure has a linear dependence with temperature, if you have two temperatures, say T1 and T2 in Kelvin, and they correspond to two pressures, P1 and P2, then you have the relation that T2 over T1 is equal to P2 over P1, right? That's just saying that they are proportional in the Kelvin scale. In this relation, P2 over P1 is the ratio of pressures in the constant volume thermometer, and T2 over T1 is the ratio of temperature in Kelvin. I cannot say it enough. T must be expressed in Kelvin for this relation. This relation does not work in other temperature scales. And this is a very common mistake to forget about Kelvin. In fact, this is the #1 mistake. Now, to define the Kelvin scale, we must discuss how to define the zero. We just discussed how to define the zero, but we need another reference point to define the scale. In the Celsius scale, we use the freezing and boiling point of pure water, but as you probably already know, the temperature of the freezing and boiling points depend on pressure. Here I show you what we call a phase diagram, and it represents the different phases of pure water, solid, liquid, gas, as a function of pressure and temperature. And at a pressure of 1 atmosphere, you see that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. But you can see that if you decrease the pressure, then the freezing point increases and the boiling point decreases. So the freezing and boiling point of water depend on pressure, and that's not very convenient if the reference point depends on pressure. So there is one point that is fixed, and it is this triple point, right? At the triple point, this is the point where you have the solid, liquid, and gas phase that exist at the same time. And this only happens at a specific pressure and a specific temperature. So we use this point as a reference for the Kelvin scale. And so in the Celsius scale, this point is at 0.01 degrees Celsius. And so we define this point as 273.16 Kelvin, so that the Celsius and the Kelvin scale have the same size degrees. So let's say that you have a constant volume gas thermometer that you want to calibrate. You prepare a volume of water and you change the pressure and temperature until you get solid, liquid, and gas at the same time. And then you use your constant volume gas thermometer and you measure the pressure on the manometer of the thermometer, and let's call this P triple. Then you can go to any other temperature and read the pressure. And you know that the temperature will be given by T will be equal to T triple times P over P triple, with T triple, which is equal by definition to 273.16 Kelvin. And P triple is the value that you measured during the initial calibration.